Okay, so this is lesson 4 for this chapter. We're going to be doing concavity and points of inflection. So what that means is we're going to be looking at the second derivative and how that's going to help us graph these functions. So let's start with a little investigation. So sketch the graph x squared. Well, we all know what that looks like. We don't need to do a huge accurate sketch. It just looks like this. There's x squared, right? And calculate the slope at these coordinates. Well, I don't think I have to do it for all of them because you're going to start to notice a pattern. But if that's the function, then we can say its derivative is 2x. So we can find the slope at any one of these points. Let's say -4. That's going to be -8. And if we keep increasing our x value by 1, you can see, -3. That's -6. You can see what's happening to our value of our slope. So -2 becomes -4, and so on and so on. So we seem to be going up by 2 every time. You can test one more if you like. Equals -2, and f at 0 would be 0, so we keep going up by 2. Now what happens if we found the second derivative then? Well, isn't that interesting? Because the second derivative is 2. Right? So remember what a derivative tells you. It tells you, well, the first derivative tells you the rate of change of that function, which tells us the slope of the function at any point. Well, the second derivative would tell us the rate of change, but it would tell us the rate of change of that first derivative function. So it's telling us how that slope is changing. Okay? And that would be this +2 here. Okay. Well, what about if our function is -x squared? So we all know what that looks like. This looks like this. Here's -x squared. Right? X squared opens up, -x squared opens down. Now if you were to take the derivative of -x squared, you just get -2x. And the second derivative would be -2. So if we tried to look at the same pattern here, and we did f prime at, let's say, -2, that's going to be 4. Okay, well, what about f prime at -1? Well, that's going to be 2. And f prime at 0? Well, that's going to be 0. So now we seem to be going down by 2, which is exactly what our second derivative tells us. So just a couple of new terminology that I'm going to bring out. We're used to saying this one opens up and this one opens down. The one I'm going to say now is this one is concave up. That's the shape. Concave up. And this one's concave down. And the second derivative is going to help us tell us what that shape looks like. But first, let's continue our little investigation over here. Sketch x cubed. Okay, well, we know what that looks like. Looks like this. Something like that. As there's f at x, which is x cubed. Okay, if we found the derivative of that, f prime at x, that's going to be 3x squared. And if you set that equal to 0, you can see that we have a horizontal tangent at x equals 0. That's right there. That's where x equals 0. Now the second derivative is going to equal 6x. Now I want you to look at something. We're going to look at a couple points, right? Because 6x, if we set this equal to 0, x also equals 0. So let's look at when x is less than 0, when x equals 0, and when x is greater than 0. Now if x is less than 0, our second derivative is also going to be less than 0. So I'm going to write this. So it's going to be negative. Okay, when x equals 0, our second derivative also equals 0. And when x is greater than 0, our second derivative is also greater than 0. Okay, so what does this tell us about before? Before, when the second derivative was positive, we got this concave up shape. And when it was negative, we got this concave down shape. So what do we know? If it's negative, we're going to get this concave down shape. And when it's positive, we're going to get this concave up shape. Okay, and you can see that right here. This one is when it's negative, and that's a concave down. And then we switch from a concave down to a concave up. At any point where we switch from concave down to concave up, or vice versa, we get what we call a point of inflection. And it looks like that point occurs when the second derivative equals 0. Now this is not always true. You're not always going to get a point of inflection when the second derivative equals 0. You have to check whether or not your concavity is changing. Okay? If your concavity changes from before and after when your second derivative equals 0, you have a point of inflection. If it doesn't, then you don't have a point of inflection. And I'm going to go over an example later of when that doesn't happen. Alright, so if we go up here, this is just a little overview of what I've been talking about. So these are concave up shapes, and they will occur on the interval where your second derivative is greater than 0. These are concave down shapes, and they will occur on the interval where your second derivative is less than 0. Now here we have a point of inflection. Your point of inflection always occurs when your concavity changes from up to down or from down to up. Right, so that's an important note to make. Over here I said a point of inflection exists if f double prime at c equals 0. I should write a point of inflection could exist if f double prime equals 0. This is called our second derivative test. And if everything goes well with our second derivative test, there's actually no need to do the first derivative test. And I'm going to show you that with some examples. So let's start down here below. We're going to finish our investigation as we are going to sketch this function here. So let me look for some space to do that. On this side, up here. Okay. So we're going to sketch, I'll rewrite the function. F at x equals x cubed minus 12x. Alright, so let's find the first derivative. First derivative of that function will be 3x squared minus 12. And you can set that equal to 0 to find any local maximum or minimum. And if we do that, we get 3x equals 12, or x squared, or 3x squared equals 12. So x squared equals 4, and therefore x would be plus or minus 2. So x equals negative 2 and x equals positive 2, we have critical points. Alright, well let's do our second derivative test here. We're going to find the second derivative. which in this case would be 6x equals 0. Sorry, 6x, but then we're going to do the test for any points of inflection by setting that equal to 0. And we get x equal to 0. So we could have a point of inflection there, but we need to test that. So let's look at the second derivative when x is less than 0 and when x is greater than 0. Well, when x is less than 0, we get 6 times a negative number. So that's going to be negative. So our second derivative then will be less than 0. So that means we are getting a sort of concave down shape like this. When x is positive, we get a positive value, right? So that means we're getting a concave up shape like this. So what that means is when x does equal 0, we get a point of inflection. Okay, so let's look at our sketch then. How are we going to sketch this? So we have the point 0, and we can substitute that back into our function, because that's just the x-coordinate, and we could figure out the y-coordinate is, well, 0, 0. So right here, we're going to have a point of inflection. Now you can also substitute your plus and negative 2, and what you'll get is, for negative 2, back into your function, you'll get the point negative 2 and 16, so somewhere around there. And if you plug in positive 2, you get positive 2 and negative 16. Now, what we did before was the first derivative test, right? We did a similar chart to this to see whether or not this point would be a maximum or a minimum. We don't need to do that anymore because we know that when x is less than 0, the shape we have is concave down. So I know it's going to look something like this. So I immediately know that's going to be a maximum point without doing the first derivative test. And then I know right here you have a point of inflection. So it looks like that. And concave up. So we switched from concave down to concave up, like so. Notice that different from x cubed, I didn't sort of move over to a horizontal tangent sort of shape here. That's because I didn't have any critical point in our first derivative where x equals 0. So that's not going to happen. So this example here, which is done for you, is similar. You have a function. First, you find the first derivative, set it equal to 0, and look for critical points, meaning where you could have a maximum and a minimum. Then you find the second derivative and set it equal to 0 to look for any points of inflection. So it looks like the second derivative would be 0 if x equals 1. So you create a chart. So you have x equals 1. Then you look for where it's less than 1 and where it's greater than 1 and what the value of that second derivative would be. We see that the second derivative is less than 0, so we get a concave down shape, which is right here. And when x is greater than 1, the second derivative is greater than 0, so you get a concave up shape, which is right here. Then you just need to figure out what those coordinates are. So when x is 1, plug that back into your original function, and you get this point. There's your point of inflection. And you can do the same to find your critical point, so your maximum min here and here. And you know when it's less than 1, you have concave down, and when it's greater than 1, concave up. And you can draw your nice cubic function there. Alright, so in this first example, I chose this example because it's going to show you how you can get a second derivative equal to 0 at a point that is not a point of inflection. So we have the function f at x equals x to the power of 4. So we can find that first derivative, and we get 4x cubed. If we set that equal to 0, then we get x equals 0. And that's easy to find the point as well. It's the point 0, 0. So we know there's a maximum or a minimum right there. Okay. We don't need to test because our second derivative is going to tell us what it is. So when we find the second derivative, we're going to get 12x squared. And if we set that equal to 0, we get a point of inflection, or a possible point of inflection, I should say, at x equals 0. So what we're going to do is we're going to test that. We're going to test it by looking at what the second derivative is when x is less than 0 and when x is greater than 0. So when x is less than 0, take any negative number like -2. -2 squared is a positive number. So that means the second derivative is greater than 0. So we get a concave up shape. Well, when x is greater than 0, so is the second derivative. It's also greater than 0. So we still get a concave up shape. So we didn't switch from up to down or from down to up. It stayed as up. So that means we do not have, so no point of inflection. But we don't need to go back and do our first derivative test because we know the shape is concave up with a minimum point therefore at 0, 0. And so your graph would look something like that. That was not very symmetric, but it's the best I could do. It should be symmetric. All right. So let's do our second example then. So we want to sketch the graph of this function. All right. So our first derivative then, f prime of x, is going to equal 1 over 3 x to the 2/3. Okay. And if we set that equal to 0, well, you can see there that x can't be 0. That makes the function undefined. So you have a critical number there. Okay? It could be, say, for example, if you remember when we did our first derivative test, it could be when the tangent goes to infinity. But we'll see more about what the shape is later after we do the second derivative test. So we have a critical number here. And if we substitute that into our original function, we have something happening at 0, 0. Okay, well, let's see if we can get more information with our second derivative test. So if we take the second derivative, we got -2 over 9x to the 5 over 3. And if we set that equal to 0, again, we get that x cannot possibly be 0. All right. Well, what about if x is less than 0? What do we have? If if x is less than 0, the second derivative becomes positive. If it's positive, that means we have a concave up shape. All right, if x is greater than 0, our second derivative is going to be less than 0. So we have a concave down shape. All right, now right here at x equals 0, well, x can't equal 0 because the second derivative does not exist at that point. So that gives us some troubles. Does not exist. But we do know a couple things. We do know that our first derivative does not exist at x equals 0. So that means the tangent sort of goes to infinity at that point. Now, the actual point exists. If you look at our function, if you plug in 0 to the original function, you get 0. So what does this look like when I draw it? Let's draw it with green. All right, so we have a concave up shape going to sort of an infinity derivative or an infinity slope for the tangent. So it's going to look like this. And then we switch to a concave down shape. Like that. So here's your concave up. Here is your tangent, which sort of went vertical at that point, 0, 0, and we switch to a concave down. So that's what our graph looks like. So just to recap, so these red lines that I drew are just there to show you the shape, that this is concave up and that's concave down, but we don't have critical points here, so that's not what the shape actually looks like. Just follow the green lines out to infinity. And also, notice that we can have a point of inflection. My mind just went blank there. Point of inflection when the function, or when the function for the second derivative is undefined, right? As long as we switched from, say, concave up or down to the opposite. Right? And we can see that this here would be a vertical tangent if you look at the first derivative and plug in a number very, very tiny in for x, and you can see that the first derivative is going to blow up to infinity. All right? So let's go and look at our last example then. Our last example is f at x equals 1 over x squared plus 3. And we're going to need to find the first derivative. So the first derivative, I'm just going to tell you what this is. You can double check it, and if you forget how to do that, just go watch one of my derivative videos. But first derivative is going to be minus 2x over x squared plus 3 all squared. Alright, and we want to see when that's going to equal 0, so really we just need to focus on the numerator then. So we have minus 2x equaling 0, which means x being 0 would give us a critical point. It's going to be either a maximum or minimum when x equals 0. So let's check out the second derivative. Our second derivative, and you can confirm this later if you want to, would be 6x squared, 6 minus 6 all over x squared plus 3 squared. And if we set that equal to 0 to do our second derivative test, again, only need to really consider the numerator to figure out when it equals 0. So we get 6x squared equal to 6, or x equals plus or minus 1. So let's do our second derivative test. It's plus or minus 1, so we're going to have to look at a few intervals. So first, when x is less than 1, when x is between -1 and 1, and when x is greater than 1. Alright, so let's look at see what our second derivative gives us when x is less than 1. So when x is less than 1, just take a number less than 1, substitute it into your second derivative, and you will get a positive value. Okay, you can see the denominator would always be positive because it's squared, right? And if you put something in here, again, you're going to get a positive value. So that means we have concave up going here. What about when x is between -1 and 1? 0 is a good number to throw in there. And we're left with that negative in the numerator. So this is going to be less than 0. So it's going to be negative. We get a concave down shape. So what does that mean? It means we switch between concave up and concave down. So right here at x equals -1, we have a point of inflection. All right, well, what about this last interval where x is greater than 1? You plug that into your second derivative and you get greater than 0. So we're switching again to concave up. So when x equals 1, we confirm we have another point of inflection. Okay, well, let's draw this. That was a terrible y-axis. All right, so we have a few points, right? We have 0, so I want to know the original function, what its value is at 0. So you can plug that into the original function over here, and you'll get a third. So that means at 0 and 1/3, let's just put that there, 0 and 1/3, we have either a maximum or a minimum. So that's a critical point. We can actually tell exactly what it is without doing the first derivative test, because at 0, right, we have this concave down shape. So that's going to be a maximum. And then we have these other points. So what's the function when f is -1? And what's the function when f is 1? So if we plug that into our function, we get a quarter for both values. So we have something over here, which would be 1 1/4. That's a point of inflection. And something over here, which would be -1 1/4. That's also a point of inflection. So we have a maximum here where it's opening down, and then it switches and opens up like that. You could also look at your original function and do your look for your asymptotes, and you'll see you do have an asymptote at x equals 0. But tomorrow's lesson, we're going to sort of combine everything we've learned in this chapter to curve sketch. Like, tomorrow's lessons will be all about curve sketching. Now let's go to the left of the y-axis. We're still here opening down, and then when we hit this point of inflection, we start to open up like that, and we go on forever, not crossing our horizontal asymptote. So that's what our graph looks like.